thanks all for coming. So today, Colin Geniet, I guess, we'll talk about something very new, like words with and chromatic number, high-boundedness, and
So-
many more, right?
Thank you very much for inviting me to talk again. Yeah, I'm very happy to talk about something which I find very exciting, which is merge width, which is a recent notion from Jan Dreier and Szymon Torúnczyk. And my excuse to speak about this is that we did some work with Marthe Bonamy doing h-boundedness for this. But really, I'm mostly going to talk just about merge width, so which is what they are on the title. So I want to say some things about motivation for merge width, but I think they might be more scary than the definition. So I will start with the definition. So what I'm going to do is describe some process to construct a graph. So this is what is called a construction sequence. So it consists of a sequence of two things. At each step you will have okay, so I should first say that the vertex set will be fixed. What we are constructing are the edges. So you will have a partition of the vertex set. And this should be E. And this will be the current edge set. So initially, quite simple. There are no edges. I didn't construct any of them yet. And the partition will just be singletons. So you start with something which looks like a bunch of vertices. Each of them is in its own bag. And there are no edges. This would be partition into singletons. Okay, and now there are two operations which allow you to go from one step to the next. The first one is to manipulate the partition. You can merge two parts. And the second will allow you to add new edges. And we call this resolving two parts, x and y, the current partition. And this means you add everything between x and y to the set of edges.
In EI.
Yes. Okay, and that gives you your new thing at the next step. Okay, so that example, I could take two parts, add every edge between them. Okay, that's just one. Then maybe merge these two parts together. Add between these two, so now it will look like that. Merge this, add the edges between them. One thing which is allowed here is they don't have to be distinct parts. So if you take twice the same part, what it means is just making a click. So I could say I'm resolving this part with itself, and that just makes this. Any questions so far? Okay, so with just this description, no matter the graph I'm trying to construct, there's a very stupid way to do it, which is, well, you just never merge anything, so your vertices remain in singletons, and then you add the edges one by one. And you can make any graph. So of course now we want to add some restrictions, and more. Rather, I should say we want to define a cost for this construction sequence, and we will try to minimize the cost. And the partitions will matter for the cost, which will give you a reason to merge things. So, okay, I this cost, I will call it the width. It's the width of the construction sequence. And okay, this is where the definition gets a bit more complicated. You need to look at every vertex. So you will take a maximum, it will be the worst case. And this is a maximum over all possible vertices at all possible steps in the construction sequence. And now you want to look at the neighborhood of this vertex in the current set of edges. And you want to say that this is small, but small with regards to the partition. So how should I write it? It's like the number of parts P in the partition such that this neighborhood intersects the part. This will be the cost locally for B. And now you look at the worst possible over the entire construction sequence. And you will try to minimize this. So you will find the best construction sequence, the one which minimizes this quantity. So this isn't quite true. I'm lying in many places in this definition, and I will fix some of them later. There's one which I need to fix right now, which is looking just at the neighbors is not actually enough to get something which is really interesting. You want to look also at the second neighbors, and the neighbors at distance 2 and distance 3, and so on. So actually what there is here is that you need to fix a parameter, which I will call R, which is a radius. So what we are defining is not really merge width, it's merge width at radius R. And where it will appear is here is instead of the neighborhood, you would take the ball of radius R in the current graph around it. So let's make an example. Imagine I do this stupid construction sequence which I described, which is you never merge anything, you just add all the edges one by one. What is going to be the cost? Well, at radius 1, you take a vertex V, you look at its neighbors, and you count how many parts this intersects. But the part has singleton, so you just count the size of the neighborhood. So in this construction sequence, right? Sorry?
In this case, the width of V, no.
What is R?
Oh, okay. So I'm.
R is 1.
You need to define.
It depends.
Maximum degree.
Plus 1.
So at radius 1, it will be the maximum degree. Right? Yes. So if I look at the width at radius 1, it would be the maximum degree. And yes, Angel is right. In this definition, we also count ourselves. So you will have plus 1. It's the size of the closed neighborhood. So what happens if you want at distance R instead? Well, instead of looking at the size of the neighborhood, you look at the size of the balls of radius R. But, well, let's say we are thinking about graphs of bounded degree, because this is what works here, really. If you have maximum degree delta, then the balls of radius R will be, I think this bound actually works. It's not tight, but it's not easy to remember. Anyway, the point is, it will be bounded by some function of the maximum degree and R.
Maybe not equals. So that's
Yes.
Thank you. So yeah, for bounded degree graphs, we get a nice one like this. And this is exactly the kind of bounds which we want to get. So since merge width, okay, so let me just first write you have merge width at radius R of the graph G. It's the minimum width at radius R over all construction sequences for G. You're finding the best one like that. So now the question is, what kind of bounds you would like for this? And here we are not, when we do this kind of thing, we don't really think about a single graph, we think about classes of graph. So what we will say is that a class C of graphs has bounded merge width. If, so you could do one thing, which is ask for a uniform bound on this, which does not depend on radius. This actually would be equivalent to click width. It's not completely obvious, but not very hard either. Here we want something more general, more fun, so we allow the bound to depend on R. So the definition will be there is a function f such that for any graph in your class, the merge width at radius R of this graph is at most this function of R. And if you think about the class of graphs with maximum degree delta, this is exactly what we got here. This is the function R. So this proves that this stupid construction sequence actually proves that bounded degree graphs have bounded merge width. Any question on that? Yes?
So far, you always considered only the result operations. About the merge operation.
So I'm going to make a second example.
Yeah.
But
There's
the
no
point
easy-
is, you will want to merge things to reduce the number of parts where it is tested. Right? If you have a graph with unbounded degree, the neighborhoods will be large, and at some point you will need to resolve all edges, so you will need to have merged things together to reduce the number of parts in the neighborhood. So, okay, let me make an example. What would be something which looks a bit like bounded degree, but is not? It's degeneracy. So, what I will show you is that if you have a graph which is D-degenerate, then, so it's not true that it will have bounded merge width, but we will get a bound for radius 1. So the merge width at radius 1 of G will be, and I think it's D plus 2. Okay, so D-degenerate, it means there is an ordering of the vertices. And now each vertex, if you look at its neighbors on the left, there are at most D of them. So now here's what the construction sequence will look like. We are going to keep a bunch of singletons, like it will be split in half. On the left half, you will just have singletons. And okay, I should put it here because. And on the right half, you will just have everything in a single part. So this will be in the middle of, I'm describing a generic step in the middle of the construction sequence. And now I need to tell you which edges already exist. So inside this big part, I will already have created all edges. And I will also create all edges going from this part to the left, but nothing in between the singletons. So now what is this this width? Well, we need to look at all the vertices. So, well, there are two types of vertices. You have vertices on the left. What is their neighborhood? Well, it's just all inside that, because we did not create any edge between this and other singletons. So this is adjacent to just one part here, plus we need to count itself, so that's just 2. Right? So no matter, it can have 10,000 neighbors here, but since it's all in the same part, it only counts for 1.
But maybe there could be a certain moment where
Yeah, there will be a
You're
slight
adding
issue
edges.
there when we are adding the edges, but let's first look at that one.
okay.
So now think about a vertex V which is on this side. Okay. What is its neighborhood? Okay, there's this part itself, that's 1. And then there's the singletons, but all the singletons are to the left, and by assumption, you have at most D neighbors to the left. So you will get D plus 1. Okay, and I wrote D plus 2 because, yes, there is a slight issue at the intermediate step. So how do you get from here to the next step where you added this vertex in the big bag? Well, first you need to add all edges from this vertex to the left here. and then move this vertex into that part. And in this intermediate step, well, you had this vertex, there's its own part, it might be adjacent to someone on the right, and at most D people on the left, so that's the D plus 2. Does this example make sense? Okay. Okay, I think it's time I stop lying, so I'm going to start fixing the definitions. So, with this notion, you can create some very dense graphs. Like, a stupid example is if you want to make a clique, you just merge everything together and add all the edges. Now, when we think about, I don't know, maybe things like over width parameter for dense graph, like clique width, twin width, and so on, generally we don't really care about edges or non-edges. What I mean is it's sort of symmetrical between them. So if we take the complement of a graph, we would like the merge width to not really change. And with this definition, there's no reason for this to be true, and actually it's possible to prove that this is false. That's not trivial, but if you take a bounded degree graph, merge width is roughly the degree. But if you take the complement of a random cubic graph, merge width will not be bounded. So we want to fix the definition so that taking the complement won't change things. And okay, imagine again this example of the complement of a cubic graph. How would you like to construct it? Well, you want to say, like if I'm trying to make the complement of this graph, I want to say this is not an edge, this is not an edge, this is not, this is not, this is not, and everything else is an edge. Well, that's exactly what we will do in the definition. I will allow you to also say that things are not edges. So I need to move things a little. There's going to be edges, and also a set of non-edges. I should start using colors. So let's say edges will be yellow, and non-edges will be blue. Non-edges. Okay. So, okay, I had an operation to add edges. Of course, I want to do the same with non-edges. So this will be called, if you add edges, we call this resolving positively. And you can also resolve negatively. Which means you are adding things to the non-edges. But now there's one thing to change, which is if I decide that, so you should think of it, initially both of these will be empty, or you should also say that. So initially your graph has neither edges nor non-edges. Sort of like you didn't yet decide whether it will be edges or non-edges. And if you decide that something will be an edge, which is what this resolve operation is, you don't want it later to become a non-edge, and vice versa. So here what you will really do is add everything between x and y, as long as it wasn't already a non-edge. And inversely, here you will add everything that is not an edge to the non-edges. So, okay, if I want to make the complement of this graph, I will say this is not an edge. Well, all of these are non-edges. Okay. Now I need to use the merging operation. I will just put everything together in a single bag. Like you do a bunch of merges until everything is in the same bag. And resolve positively this bag with itself, which is you make it a clique. Except for the things which were already non-edges, which will not change. So this is how you make the complement of a bounded degree graph. And the width will just stay the same. So with this fix, oh, sorry, the width. I did not define the width. So how do you change this definition? Again, we don't really care about edges versus non-edges. This should be symmetrical. So here I don't care about the distances in the graph. I care about the distances in the things which I already resolved. So it will be edges and non-edges. So you can, it's something we call the graph of resolved pairs. It's everything which has been resolved. So the edges on this graph would be this union. The non-edges are the things which you did not yet decide. And this is where we measure distance instead of measuring them in the graph. Any question?
The sequence ends when everything is literal.
Well, you think of it as you're trying to construct some graph. So as soon as the current edge set is the edge set of the graph, you can declare that you won. You can change it and say you need to resolve everything. It doesn't actually change anything because at the end you can always merge everything together and say that what remains is a non-edge. So you can make a few variants and they are completely equivalent. Okay, so let me start talking about motivations. So
Is there some situation where you have to resolve edges positively and negatively before, or can you always do it in this way, like add edges and then at the end it's just say you're done, or add non-edges and then say
I don't have an interesting example. I can make plenty of stupid examples, like taking a cubic graph and the complement of a cubic graph and putting them together with multiple ways of putting them together. And
okay, that you can probably make that interesting.
you can do a lot of things with only this positive resolve. And I'm going to say more about that. But okay, so what is the one goal of Jan and Szymon in their life currently? It's what is called the first order model checking problem. And this is about logic. Sorry, I'm going to start saying scary words. So it's not a very weird problem to think about. The name is a bit weirder. It's an algorithmic problem. You are given two things, which are a graph and some property which you want to test, and this property is written as a first order formula. A formula in first order logic. First order means you can quantify on vertices, so say there exists a vertex for any vertex and so on, and test if two vertices are adjacent. It's sort of the simplest, most stupid logic on graphs that I can think of at least. So you have a graph, you have a formula, and you want to test if G satisfies this condition. So for instance, with first order formula, you can write there exists an independent set of size k. You say there exists vertex 1, vertex 2, vertex until k, and none of them are adjacent. So this generalizes testing if there's an independent set of size k, or testing if there's some specific induced subgraph. Okay, and what would be the obvious algorithm for this problem? So first I should say we care about the parameterized complexity of this problem. So we will say, let's say n is the size of the graph, number of vertices, and k the size of the formula, or usually what we really care about is the number of quantifiers in the formula. So if you look at the naive algorithm, it will be in time n to the k. Because for each quantifier, you will just go over all the possibilities, go over all the vertices. And this just works. So the goal is to do better than that. And okay, we're doing parameterized complexity, so we want something which is fixed parameter tractable, FPT, meaning some function of k, some like really bad function of k, these will usually be, well, these have to be tower of exponentials at least, times a polynomial in n. But the point is that this polynomial should not depend on k. Okay, so under standard complexity assumption, this is not possible to do for all graphs. Like this model checking problem is complete for a weird complexity class which is called AW star, which is the complexity class for this problem, and I don't know anything else which is complete for this problem, for this class, sorry. But yeah, it's somewhere in the FPT hierarchy. It's above the classes WK for any k, if you know what this is.
So in particular, this allows you to, like you said, to test if the graph has an independent set of size k.
Yes.
So is this already hard according to?
Independent set is hard for the class W1.
Okay. So
It's like the hierarchy of class. There's FPT, which is sort of the equivalent of polynomial time, but in the parameterized hierarchy. Then you would have W1, which would be the first one just above, where you find independent set. W2 is also famous because you have a dominating set. People doing graph theory have no idea what's going on beyond W2. I don't know any problem in graph theory which would be in a class above that. That's probably not true, but well, no, it's true. I don't know any. And then there's this AW star, which only people do in logic know because of this result. And then even beyond that, you have XP, which is this precise complexity. Okay, so we assume that this doesn't collapse, or in other words, we assume that this problem is not FPT for the class of all graphs. So then the question they have is for which classes of graphs is this FPT? Okay, and well, of course, Marthe is here because it's related to this problem. So the big result that they proved is that I'm not going to state it very formally, but if C has bounded merge width, then this problem, which is too long to write, so I just write first order model checking, is FPT with some very big small print, which is, so what they prove is if you have a construction sequence, it helps you to solve this problem. We don't know how to compute the construction sequence. So if we are given, or we know how to compute good construction sequences. Good meaning witnesses of, they don't have to be optimal, but they should satisfy this bound for some function. So how does that, I'm not going to get into any detail, but let me give you some intuition about how this kind of result is proved. Let's imagine, okay, I will draw, no, that's not very good. So if you have a construction sequence, it gives you a sequence of structure where you have the vertices, which don't change, and then you have the partition, edges, and non-edges. And initially, it's a fairly trivial structure. The partition is into singletons. This is empty. And what you want to do is solve this problem by dynamic programming over this sequence. So you start from the first structure where solving this will be trivial on an empty graph, and you update it when going to the next step. So you won't exactly solve this problem because if you think about a fixed formula phi, the induction is not going to work whatsoever. What you want to do is, in some sense, solve the problem for every formula phi of a fixed size at the same time. More formally, this is what is called logical types. We define what is the type of a vertex. It's all the information about this vertex which you can describe by formula of a fixed size. And this is the robust notion when you want to do this kind of dynamic programming. So really what you do is compute the type of all vertices and then update going to the next. And okay, updating is far from trivial. There is some really non-trivial results about logic which are used in there. But in the end, from the merge width point of view, what the algorithm is quite simple. It's more preparing by doing a lot of work about logic, and then you have these two operations to update your graph, and for each of them you need to update the types. Okay, so that's nice. We can do this problem for merge width. That's not quite enough to say that merge width is interesting. So now what I want to tell you is what is known about this problem in general. And okay, here the people who were at the combinatorics summer school 2 weeks ago will have a very big advantage, because this is exactly what Mirao was talking about. Okay, if you have a good memory, Mirao was also giving a seminar here back in November, and this is also what he was talking about at this seminar. So I will give a very, very short version of this talk. So there's a big conjecture about this problem, which is that the classes for which it can be, for which this problem is FPT, is exactly what are called dependence classes, or monadically dependent for first order logic, if you want a long name. I'm not going to define that precisely, but the idea is dependent means you are not equivalent to the class of all graph up to first order logic, whatever that means. It means transactions. So the idea is if you are equivalent to the class of all graphs, then this problem is going to be hard. It's going to be as hard as in the class of all graphs, and we assume that it is not FPT in that case. Proving that this is actually, that for classes which are not dependent, the problem is actually hard is very hard. But it is a theorem now, quite recent one. So the conjecture is if you don't go beyond that, if you are not equivalent to the class of all graphs, if you are not very, very complicated, then we should be able to do this problem. This is very much open. But okay, studying this thing started from, well, much smaller. So this is the most complicated. I will start with the simplest stuff. Historically, I think it started with bounded degree graph. This result of César is from the 90s. So bounded degree is very nice about for first order logic, because in some sense, first order logic only talks about bounded radius. And if you have bounded degree and bounded radius, it means bounded size, and that's always very helpful. So yeah, César proved that there is such an algorithm for this. And the other first line of research was things like planar graphs. This is from Grohe, and I've always mixed up, it's either Flum or Frick. Planar graphs, and then the generalization would be KT minor 3. So all of these things are very sparse notions. And I did my table way too big because I'm not going to use that much space, but okay, yeah. I will write big. This was all in the 90s or early 20s. And much later came a very big generalization, which is from what's called the theory of sparsity, from Szymon and history. And this is based on two notions which are called bounded expansion. And yeah, I really took way too much space. There will not be anything here. I'm sorry to disappoint you. And the second is nowhere dance. So bounded expansion is a generalization of both of these things. It's a very, very big generalization. I will give you not the definition, but some intuition on what it means. And yeah, nowhere dense is even more general. So these are more recent results from around 2015. These two. And so there was this result about doing such an algorithm for nowhere dense. And this is actually the best which is possible in the setting of sparse graphs. The formal statement would be if you look at subgraph closed classes, then being dependent is the same as being nowhere dense. And if you go beyond nowhere dense, well, it means you are also beyond dependent, and then we can prove that the problem is hard. But then more recently, well, after doing this, people started asking, okay, we did sparse graphs, what about dense graphs? And okay, for a time, not that much was done. So something which people started looking at is, I'm going to put it in parentheses because I don't really want to talk about it, but there's something in between nowhere dense and dependent which is called stable classes. Stable, intuitively, it's graphs which are dense but behave like sparse graphs. We watched a video from Rose McCarthy a couple of weeks ago. She was exactly talking about this, how model checking works here. So this is also known. But yeah, there's one line which Mira drew and I'm not going to do, which was everything about stable graphs. But okay, I'm not talking about this, I'm talking about really dense graphs which don't behave like sparse graphs whatsoever. And for a very long time here, the only thing we knew was click width. So for click width, we can solve this problem for a sort of stupid reason, which is that we can solve a much harder problem, which is the same thing with monadic second order logic. This is Kurzweil's theorem. Monadic second order logic means you are allowed to quantify on sets of vertices. This is way more powerful. It allows to talk about things like connectivity or coloring, which you cannot do, really cannot do in first order logic. And there was, for a long time, this sort of stupid situation where we could do this for click width because we can do something more general. And for really dense graphs, we did not know how to go anywhere beyond this. Like first order logic is much more restrictive, and yet we did not know how to do more than that. So like click width is from the it's early 2000, right? I'm not saying nonsense. And 20 years later came the first progress on this line, and this is twin width. And now what is the idea of merge width? Is well, since, so twin width was 5 years ago, and since then people have been asking all the time, it would be nice to have something which is twin width, which is the best we can do on this line so far. And bounded expansion, which is a really, really nice notion in the sparse set. Like, nowhere dense can be a bit harder to understand. Bounded expansion is really nice, has a lot of equivalent characterization, which are very nice to work with. And this is what merge width is. So, yeah. This is the first big theorem about merge width. You can do this model checking. The second big thing is that it generalizes both twin width and bounded expansion. So let me try to convince you that this is true. I'm going to cheat a lot to convince you. Let's start with bounded expansion. What is bounded expansion? The idea is that it's a bit like degeneracy. It means you are degenerate. So it's a stronger condition than degeneracy. You are not just degenerate, you are degenerate at radius r. For all r. Degenerate at radius r, the actual name is something called weak or strong, there are two variants, coloring numbers. But these are really the good generalization of degeneracy. So just like merge width, these are things which are parameterized by a radius. And then you want the same kind of condition as here. It's this at radius r will give you some number, and you want that it is bounded by some function of the radius. So why does bounded expansion imply merge width? Well, you take the proof for degeneracy and you do it for radius r. I'm cheating, it's actually a bit harder, but that's essentially the idea. So yeah, degeneracy gives you a bound on merge width at radius 1. This weak coloring number at radius r plus 1, I think, will give you a bound on merge width at radius r. So if it is bounded for every r, merge width is also bounded for every r. Okay. So now let me talk about twin width. I'm going to cheat even more. I'm just going to come up with a definition of twin width. It is actually equivalent to twin width, but I did not tell you what twin width is, so yeah. It's actually quite simple. Here what we did is, for every vertex, we looked at the ball of radius r, and we count how many parts it intersects. So let me draw it here. I will just do it at radius 1, but you have some parts, some vertex v inside it, and it has some neighbors. And okay, maybe it has a very large number of neighbors in one part. This is fine, it just counts for 1. Here, but this will just count for 3. But what could happen is that if you take a different vertex in this same part here, it will be adjacent to different parts, let's say. And yet, then you take yet another one, it will again see different things. So if you don't count around just one vertex, but around this entire part, you could have neighbors in the very large number of parts. This is what you forbid for twin width. So twin width, what you do is, instead of counting over maximizing over all vertices, you will maximize over all parts. And here, look at the ball around this part. So like merge width, you are looking at this thing. Twin width, you will look at all of that and count how many parts this intersects. So of course, this is more restrictive. Okay, so that's the two big things about merge width. And I should say the third one is that it's a well-behaved notion. It's stable under many operations. One of them was this complementation. More generally, you can do what's called first-order translation, and this will present having bounded merge width. Yes, you had a question.
Yes. Will you draw these edges? They include both EI and NI, or just EI?
Oh, yeah, it's edges and non-edges. Oh, and I said I would say something about only positive result. So yes, if you have bounded twin width, you do not need non-edges. And for bounded expansion, you don't need them either. When I did the example for degeneracy, I was only resolving positively. This also works for recurring numbers. So yeah, you can actually capturing both twin width and bounded expansion. You can do this already with just positive results. But getting nice stability properties is the reason we want to also keep the negative ones.
But what do the red edges in between width correspond to here? These edges that get contaminated during the composition?
It's the way to think of it is, as long as you don't have red edges between two parts for twin width, you don't need to resolve anything for merge width. And when you see that a red edge is going to appear for twin width, for merge width, you stop just before that and resolve something. But roughly speaking, red edges and resolved edges will be the same. Like, okay, red edges are between parts. You will have a red edge between parts for twin width if you had some resolved edges between the vertices of these two parts.
Ah, okay. If between two parts I had both a yellow thing and a blue thing here, then in the twin width kits it should correspond.
If you had either of them, and actually you can do it with just blue edges, so if you have blue edges, then it will become a red edge.
If I just had blue edges between two parts?
Well, what I'm saying is you never need to create all the non-edges. You can always delay them until the end.
Ah, okay.
And for twin width, this will not really change.
Because you have to pay some extra
Probably, yes. I'm not sure, but probably.
But is it always true that the twin width is at most not true? But then I also need to be
No, the other way around. If twin width is small, then merge width is small.
Merge width of rate is 1.
So twin width is not parameterized by your radius, but the reason is you could define twin width parameterized by your radius, but then if you wanted twin width at radius r, it would be bounded by twin width at radius 1 to the r. But okay, if you do this parameterization by your radius, then merge width at radius r will be bounded by twin width at radius r up to very small constants. Any other questions? Okay. I'm supposed to say something about χ-boundedness, otherwise I'm not allowed to do this stuff, right? So, I want to say something about χ-boundedness, but really the reason is that it's a good excuse to do some proofs to manipulate merge width. I gave you a few examples of how you would construct a construction sequence, like how we prove that degenerate graphs, for instance, have a bounded merge width at radius 1. So now I want to show you how to use it. Of course, there was one example on how to use it, which was this model checking algorithm, but that's quite complicated and was quite abstract. I'm going to do something which is much more concrete. So yeah, what we proved with Marthe is that I don't even remember the bond, sorry. Yeah. The classes of bounded merge width are χ-bounded. Χ-bounded means, yeah. So let me just write it for any graph G. Chi of G, the chromatic number, so this number of colors to properly color G. Well, we want to say that this is good in bounded merge width classes. But of course it can be extremely high because you can just make clicks and they have merge width 1 at any radius. So the usual notion of chromatic number is good even if your dance can contain click is χ-boundedness, which is if you do not have a large click, then the chromatic number is small. So what we prove that it's bounded by a function of the omega of G, this is the size of the maximum click. And merge width. And here you don't need something fancy about being bounded at every radius. We just do it for radius 2. Okay, I'm not going to prove all of that because, yeah, I'm going to be short on time, but so I guess, do you have a question?
Is there anything, did you figure out what, like, is the function a crazy tower of twos, or?
Yeah, it's not quite, no, I think it's just exponential, not a crazy tower. I think. Don't quote me on that. No, I think I actually wrote the function somewhere, which I would not have done if it was.
And if you wanted
No,
to
I'm
make
not,
it
I'm
valid,
really not sure. Sorry, yes.
and if you wanted to make, instead of 2, have some other integer, this would still be open? Or I'm not quite sure I understand the implications so well. If instead of 2, I want, say, 14.
Oh, that's easier. If a merge width at radius 14 is bounded, it certainly is bounded at radius 2. Right? At radius 2, you are looking at smaller balls.
Yeah, okay.
So that is a question, does it work for radius 1?
Yeah.
This is open. It's the small open question for around this theorem. So, okay, I'm going to pull out some magical conditions, some magical extra assumption, and prove χ-boundedness when using that. But this is not for no reason. This is actually the proof of this theorem is in 2 steps, and I will do one of the 2 steps. So Yeah. Okay. So this will be a condition on the contraction sequence. I will look at contraction sequences with a specific form. So I say that construction sequence, contraction sequence is formed between it, and I always mix up the words. So construction sequence is, okay, and I really don't have a good name for this, but I call them structurally omega bounded if whenever you do a positive resolve between two parts x and y, then you want them to be independent sets. No edge inside X or inside Y. And this is not in the current graph, this is in the Fiedler graph, the one you are actually constructing. So in particular, this means you cannot, I told you in general for matrix, you can resolve a part with itself. Here you will not be able to resolve a part positively with itself, because if you do, then it's not an independent set. So this is not allowed.
I thought this is the condition before resolving.
No, this is on the final graph. Like the actual graph you are trying to construct at the very end, not at the current step of merge sequence. So, okay, this is a weird condition when I just write it like this, but reducing the point to that is not that hard. Like it's half of the proof is reducing to that, the second half is proving it for that. So the reason I call this structurally omega bounded is this condition, like it's a condition on the structure of your construction sequence, and it will imply that the clique number omega is bounded. So this is where this stupid name comes from. So let me just, I'm not going to use this, but I want to show it because it's, it gives you an idea of how the proofs work. So, if you have such a construction sequence, the clique number of the graph will be at most the width at radius 1. Okay, why is that true? Imagine you have a big clique in your graph. And now look at the first moment where, so initially all of these are in singletons, and at some point they are going to be merged together. I can always assume that in the end everything is merged together, so the worst case this will be at the very end of the sequence. So at some point, I'm about to merge two of them together. Now, a consequence of this condition is that since these two things are adjacent, once you merge them, you cannot add any new edges. So before I contract and merge them together, I need to have already created all of these edges, right? So let me do it in blue, since that's the color I use for the current resolved edges. All of that will need to be created before merging them.
Wait, I'm confused. So what if I just keep merging, and so that in the end I have only one part, and then apply single.
But you're not allowed because it's not independent.
No, I did. Oh, I see. It's in the final graph. I see.
Final graph. Yeah. This pair. Okay. Oh, by the way, initially they are singletons. Maybe they will be merged with a lot of other stuff. That's not an issue. What I care about is when two of these parts will be merged together. Right? So actually the picture should rather look like that. But yeah, as soon as you merge two parts together, you're not an independent set anymore in the final graph. So you cannot do any positive resolve. So you cannot add edges anymore, which means you need to already have created all the edges. So it will look like this. And now just before we merge this, you look at what is the close neighborhood of this vertex, and you will have as many parts as there are vertices in the clique. So the width at radius 1, exactly this, will be at least a set of this clique. Okay, so this we don't use in the proof, but what we use is that same assumption. I take any construction sequence to satisfy this condition, then the chromatic number, which is what we want, is bounded by the merge width not at radius 1, but radius 2. So how did the proof work here? It was quite simple. You just looked at one specific moment in the construction sequence. Like take just the right partition, and then think a bit about the conditions you have on the definition of merge width, the extra condition we have, and it gives you the bound. Here we need to be more clever. So one way to think about a construction sequence is, okay, let me write horizontally, these are vertices, and vertically, this is the time. And so what happens is initially you have all your vertices here, they are in singletons, and you're going to start to merge them. Right? So like here they are, this is one partition, so here all of these would still be singletons. Okay, and I'm going to start cheating and skipping steps, so I will merge several things at once, otherwise it will be too long. But yeah, maybe your construction sequence will look roughly like that. And on top of that, you are at some point resolving stuff, so adding some edges, like maybe things like that. And, yeah, there might be non-edges as well. Stuff. This was not allowed because this is not independent anymore, so this I would not have been allowed to do that well. Oh, sorry, I think I mixed up. No, this was correct. Okay, this one, this I used the wrong color, sorry. Yeah, so for this proof, we just picked the right level somewhere. And for this lemma, we need to do something a bit more complicated, which is pick something more like this. Pick an anti. This is a tree. Oh, it is just a weird way to draw a tree where this is a node and these are its children. And you need to pick an anti-chain in this tree. So, in other words, I'm going to pick a bunch of parts. And the condition you need, so I'm defining a new partition P by using this construction sequence. And it will consist of maximal parts at some point in the construction sequence, at any point. I'm doing this, not doing this for any for a fixed I. It's like you look at all the partitions in your construction sequence. You take the union of that, so it gives you a very big family of subsets of your graph. And now in this, you care about the ones which are maximal and are involved in a positive resolve. So in this example, like this is here there is a positive resolve, but it's not maximal because this one is bigger and also. So I would pick that one, and I guess this one, and okay, this was an isolated vertex. Let's give it a neighbor. So that one as well, and these parts which are color wide, this would become my partition P. So what can you say about parts in P? First thing is it's an independent set. Why? Because which shows things which are involved in a positive resolve, And the magic condition here says, in that case, you must be independent. Okay. First point. The second point.
So this, you're assuming this construction sequence is also structurally omega bounded.
Yeah.
I
Yeah, I'm
see.
still doing it under this same assumption. Yes. Notes. Oh yes. The second point is imagine you are taking apart. So you take a part in this partition which we care about, but we care about when was it created. So it was created by some partition at time I. Then what you have is that this is your part P, and at time I we know we resolve this with some other part. So in particular, you will have some vertex here, which is resolved with everything in this part P. I'm slightly cheating in this drawing because maybe there were resolved non-edges in it. But I don't care. What matters is that there is a resolved something between this vertex here and all of P. Okay. And now comes the nice argument, which is something about degeneracy. So imagine I'm drawing the partition P, and I'm ordering them according to when the part was created. So I want to start with larger parts. So these were created larger. Intuitively, they should be larger, but that doesn't actually have to be the case. And the parts get progressively smaller. What I claim is that in the graph G,
So
sorry,
the
yes.
blobs on the right, they were created before the one
Yeah.
on the left?
This in this drawing, this would be the bottom, and this would be the top. What I claim, so we know that each of these is an independent set. I claim that if you take the quotient of this graph, this will be degenerate for this specific ordering. And this this gives the bound on time. Okay, so why is that? Well, I'm taking a part P. So it's my same part which comes from time I. And now I need to draw a second thing, which is there was this partition at time I. So this was also a part at time I. And what will it look like here? Well, these were from time after I. So here the partitions from PI will be, the parts from PI will be smaller, right? It might look like that. And here it's the other way around. This came from earlier, so the parts from time I would be larger. It's like here, partition PI is horizontal, and partition P is a diagonal going like that, if I ordered it correctly. Okay. So I want to say that there are few neighbors on this side. So imagine I have an edge to this part. And now I'm thinking about the edges at time I. I know that this edge must be resolved. Why? Because I picked the last moment where we resolve positively the part P with something else, right? If this edge was not resolved at time I would need to resolve this part with something else later, and then that just wasn't the correct part to pick. So it is resolved. And then I use this second thing, that there is a, like, P was completely resolved with something somewhere. So let's say, for instance, this part here, right? This is completely resolved. So if I take a vertex here, what happens? It is adjacent to everybody in P. So at distance 2, it is adjacent to this here through resolved edges. But we know that at time I, if I look at the ball of radius 2 on this vertex, you don't see too many things. So you don't see too many parts, but for which partition? It's the partition at time I, which is these red things. But that means P cannot be adjacent to too many red parts here. And then the white parts are bigger, and the white parts are the one I care about. if you are not adjacent to too many red parts, you are also not adjacent to too many white parts. And this is the degeneracy proof. There should be a +1 or +2 here. Sorry, +1 probably. Okay, so I'm out of time. Sorry, I'm already over time, but yeah. Reducing to this is sort of the same kind of arguments. There's again picking the right partition, which is not just one time step, but an anti-chain in the construction sequence, and some induction on the side of the maximum peak.
So what's the statement? You can, so whenever you have a construction sequence with witnessing radius are merged with, then there is structurally omega bounded one, which is again
No,
radius.
no, it's not that simple. So it's a reduction for χ-boundedness. So the statement, the lemma would be, you give me a merge sequence at radius 2. I'm going to partition the edges of the graph into 3 classes. And partitioning the edges is good for chromatic numbers. So okay, there will be 3 things. There will be one with a smaller clique number. So this will be an induction of the clique number. Okay. There will be one which satisfies this condition. It's like it will be a subset of edges, but you can keep the same merge sequence. And now this merge sequence will satisfy this condition for this subgraph. And the third class, there will be a degeneracy argument a bit like this one, which works fairly directly and shows that.
Okay, so you cover the edge set with the better properties. So one
Yes.
of them is this.
So I'm sorry for being out of time. Do you want 3 open questions?
Yes.
So, very quickly, stupid open question, replace 2 by 1 here. I believe it's true, I believe it's going to be very annoying to prove. Stupidly hard open question, proof of polynomial χ-boundedness. So this function here, we would, when this is fixed, or no, you don't have to be hardest 2, but when we fix a class of bounded merit, we would like it to be polynomial in omega. We know that this works for in this picture. Okay, χ-boundedness is stupid on the bottom line because these are things. Sorry, let me. This is not optimal. Things up to bounded expansion, they just have bounded chromatic numbers. So χ-boundedness that makes sense. This is polynomially χ-bounded. So we see the reasonable question here. This is not χ-bounded at all, so the question does not really apply to this column. Okay, these are the χ-boundedness questions. The big question for merge width is, in general, how do you prove that something has bounded merge width? Because, okay, we did some simple examples, and for simple examples, you can just construct the construction sequence by yourself. But in general, that's not the right approach when you want to do hard things. Like for twin width, for instance, the definition of twin width is very similar. It's called construction sequences. And again, simple example, you can just do your construction sequence. But for hard ones, there are some kind of duality theorems on characterization with obstructions. And this is really what is missing for merge width. We know how to use merge width, we don't really know how to either prove that it is bounded or it's essentially the same thing, how to use the fact that it is not bounded. Thank you very much. Sorry for going over.
Thank you. Any questions? Yeah, Linda?
I mean, this is maybe a bit random question, but for twin width, right, you could prove polynomial χ-boundedness by showing you have, by defining this operation, delayed extension. Do you think there's any hope that there could be such a pretty operation that characterizes merge width?
So it does not characterize twin width.
Sorry,
But,
characterize is the wrong word, but it
Yeah.
captures.
Hopefully, yes. I have no idea. The technique for twin width is the decomposition are very related to having a good ordering of the vertices, which is exactly what twin width is about. So it's really not obvious how to generalize that. I don't think polynomial k-boundedness is just going to fall out of nowhere. So yeah, we probably need a really nice notion like that. But I have no idea what it could look like.
Is there an equivalent way of looking at merge with from the matrices lens? Like,
No, precisely that's the issue. We have this for twin width, we don't have it for merge width. But that is what I meant by a kind of duality theorem.
I mean, duality theorems are also with matrices, but this matrix version of the grid liners. But matrices are also used to define these contractions. Like you can also define a contraction sequence on a matrix.
Oh, okay, sure. You can define merge width for matrices, that won't be an issue and it will be equivalent, yes.
Is merge width defined for logical structures as well?
The binary structures, yes.
Only binary.
Non-binary, I have no idea. It's even twin width is very iffy for non-binary structures. So no, for the general, for binary structure, it's very easy. It's you just edges, non-edges. You have as many variations as you want.
Okay.
A few more sauce.
Right, any other questions? So if not, let's take the
Oh, I forgot flip width, sorry. Yeah, that was the last question.
What was it?
There's something here, like the first attempt at